let's start our lecture. Now let me recall that the previous time we construct spectral sequence from a filtered chain complex. If we have chain complex and we have increasing filtration on this chain complex, such that this filtration is locally finite in each degree, then we construct spectral sequence of homological type, which starts from homologies of quotients and converges to homologies of the original complex. Now maybe here I need to say that if you have degrees in filtration or in co-chain complex, if you have co-chain complex, and you have degrees in filtration, then all this construction works, and you obtain cohomological type spectral sequence. Cohomological types. This means that differential here, R differential has B degree minus R minus 1. And homological type spectral sequence means that differential has degree R 1 minus R in the opposite direction. Now all properties are the same and construction is the same, and you obtain homological type spectral sequence of the same form. Where first is cohomology of quotient complex. The first is cohomology of the quotient, and this is co-chain complex. It's important. Here differentials also increase degree. And it converges to cohomology of the co-chain complex itself. Now, if you have another direction of differentials and another direction of filtration, then if you, for example, have increasing filtration in co-chain complex, then you just re-index chain complex and you obtain chain complex. But if you have it's just convention of standard indexes. Because they are often arise in practice. And we consider today I will consider only homological types, and all homological counterparts I will leave as an exercise. We consider our main example if we have B complex, for example, homological type. Then we can consider the corresponding chain complex as total chain complex. And on this total chain complex, we have two standard filtrations. It's horizontal filtration and vertical filtration. And they give us two spectral sequences, first spectral sequence and second. The one have homologies of your B complex modular vertical and horizontal, and other is homologies of horizontal and vertical differentials, and they both converge to to homology of the total complex. So they converge to the same thing, and this will be crucial today.
Why do we write number 2 there? I mean, can't we just say that our list is...
No, it's the second page. No, you can. No, I mean that it's the second page. So on this page, you already have differential of the b degree of this b degree. Okay. Number of page, it's b degree of differential, so it's important to remember the number. It's not 0 page in sense that it's this b degree of differentials. You also have 0 and first, but no, the most important the second page, because this page depends only on homologies. Okay. Okay. Okay, let's apply this construction. Let's consider two modules. No, now I want to consider a Tor between them. So one of them is left and one of them is right. And I have projective resolutions of one module and another module. Now, for example, this is right module, this is left modules. Okay. If I, the reminder that if I have two chain complexes, I can consider their tensor product, and this is B complex, okay? If I have two chain complexes, I have their tensor product, and in fact, no, it's chain complex, but in fact, it's total complex of some B complex, yes? So, now let's consider this B complex. And consider two spectral sequences of this B complex. The first one, I have. Okay, let's start from the beginning. 0 page of the first one, where I consider quotients, for example, for this index. Okay, it's it's by definition this thing, where I consider the the first differential, for example. Okay. Okay. Just 1 second. Just one. Yes. No. Okay. No. In fact, it's not very important. It's the first or the second. Okay. No. Let's. Okay. If you want, if you wish, the vertical one. Yes. Yes. No. If you consider, what if you consider homologies of this complex? You consider some resolution and tensor. No, it's Tor, but no, of course it's Tor. But okay, you're right, it's Tor. But P is projective, so it's flat. So all Tor are zeros. Okay. No, it's the same thing. So if module is flat, then tensor product with it preserves exactness. So in fact, all homologies are zeros except the last one. So yes, you're right. It's 0 if Q more than 0, and this is tensor product of P tensor with homologies of in zero. What homology in 0 degree of resolution is module itself. Okay. So the first page of the first spectral sequence is, no, I have only Q is 0, it's only one row, and Q is 0. And in this row, I have resolution with n. And now I have the differential is just differential in P. Okay? And if I compute its homologies, what the second page? No, now it's Tor. You're right. It's Tor in each degree. Tor between m and n. So the second page is the same row, 0 row, and in p place I obtain p Tor m and n. Okay. What about the second spectral sequence? In general, let me just recall what the second spectral sequence. I have 0 page is the same thing. But now my differential is vertical. So maybe you're right. No, it's just about that. If my now I want to consider this differential, and maybe now no, but I need that the 0 differential is horizontal, yes. So maybe I need this reindexing here. Maybe you're right. Let's do this. Okay. No, because I want to consider this horizontal differential, but by my definition of homological type spectral sequence, in 0 page it must be vertical. Okay. So it's just reindexing of this, and then in my this thing it was q p h p h q okay. No, it's okay. It's not important in this exercise, but maybe no. Let's remind this. Okay. Homology. What the homology? No, the same thing. But now, so homology. It's m tensor q if p is 0. So again, I have p is 0, and now p is number of columns. So okay, again I have m tensor q. This is q. And again, the second page, I calculate these differentials, and I obtain the second page of this spectral sequence. I obtain. No, but okay, sorry. What I wanted to check now. It's not Tor. I don't know what Tor is it in fact. It's homology. It's p homology of p tensor n. And this is q homology of m tensor q.
Why is it not Tor?
Because it's what I want to prove now, that these two definitions of Tor coincide. Okay?
No, I guess you wanted to say that this is Tor mn, this is Tor nm, and they.
No, this is Tor mn, and this is Tor mn. I cannot change the order because my R is not commutative. But I left this to further lectures in the definition of Tor. That these two definitions coincide, and now I improving this. Okay, I'm proving now that if you consider Tor projection resolution of one module and consider this thing, and then calculate homologies, and if you consider this thing, and now now I'm proving that they coincide. In fact, it's not obvious, but it's obvious for a spectral sequence because here I have this homology and here I have this homology. In both spectral sequences, all other differentials are 0 because I have only one row and all other differentials again already 0. Okay, by degree reasons. So this is in fact infinity page. Why it's first? Why it's second? Infinity page. The same thing. And this is also infinity page. And now, again, this the main observation that if you have spectral sequence with only one row, then filtration on the target, on homology of total complex, has only one non-trivial filtration in each degree, because in each diagonal I have only one non-trivial element, okay? Now again, because in my target graded object I have filtration, and quotients of this filtration isomorphic to infinity page. And if I have only one non-zero infinity page, and I know that this filtration is finite, in fact, then in fact it's stabilized, and it's for less enough, for small enough indexes, it's all whole homology. For big enough indexes, it's whole homology. For small enough, it's zero, and the only one place when it's not equality here, because only one place where the quotient is not zero, okay, between these two filtrations, okay? No, it's the same observation. I have filtration, and quotients are my infinity page. What?
What are you trying to explain from that?
No, that this is homology of total complex. It's obvious, because on homology of total complex I have filtration. On homology P plus Q of total complex of P tensor Q, I have some filtration, some increase in filtration. Fp minus 1, and quotients is my infinity page. But in my infinity page I have only one non-zero row. So here it's fixed diagonal, fixed P plus Q, it's fixed diagonal in the infinite page. And in each diagonal I have only one non-zero element. So in this filtration only one non-zero quotient. So only one not strict inclusion, okay? And all are inclusions strict because all other quotients are zero. So in fact, and I know that for small enough it's for big enough it's just my whole homology, and for small enough it's zero. So in fact it's 0, 0, 0, 0, then my infinity, and then equalities to my whole homology. So in fact my whole homology is infinity, okay?
Yes, but this is just okay. I agree, but why do we need to like say it? Okay. So we had we know that this spectral sequence of total complex converge to
yes.
this homology. Why do we need to state it once again?
What? No, I say in general, in general situation, if you have spectral sequence with only one non-zero row, then these elements in this row it's your target elements, because in your target you have some filtration, but it's not total. Maybe its target is something, and you have filtration. And quotients, if it's elements of this fixed diagonal in your infinity page, of elements of this diagonal on your infinite page, okay? And if in each diagonal there is only one non-zero element, then only one quotient here is not zero. So in fact you have equality, then some submodule with quotient infinity, and then again equality. But in fact here is zeros. So in fact this submodule is zero. So in fact you have HP plus Q modulo 0, it's infinity. So in fact they are equal, and you have equality, then 0, 0, 0, and all these modules are at the same time HP plus Q itself and infinity PQ. Okay, it's obvious. Okay, no, it's the main observation. So if you have two non-zero rows, then you obtain long sequence, as we see for spectral sequence for filtration of length 1, and we obtain the long sequence in homologies. In fact, if you have two non-zero rows, you obtain long sequence because you have some short sequence, some extensions. But here all extensions are trivial. You have only you have trivial extensions, only equality. It's not extensions here. If you have two rows, you already obtain some extensions, some short X sequences. And maybe you can glue them together to one long X sequence and something like this. But here, if you have only one row, you just have equality. So in fact, you obtain that Hn of PQ. No, it's here. It's not complex. It's total complex. It's chain. It's standard product of chain complexes. Okay, it's chain complexes. Total of the corresponding B complex. It's isomorphic to E infinity the first. No, on nth diagonal, only one element in 0 row. It's 0n. Yes. No, it's n0. Sorry. Yes. And this is nth homology of here P. And it's isomorphic to at the same time to the infinity nth of the second spectral sequence, and it's sorry, no, 0n, sorry. Okay. It's nth homology of M tensor with Q. So we obtain that these two definitions coincide, okay? And in fact coincide with, you can consider two, no, this is more symmetric definition. You have two, you can consider two projective resolution, consider the tensor product and calculate its homologies, and you obtain Tor. No, so this homologies coincide, and we call these homologies nth Tor between M and N, okay? Okay? And so for commutative ring, if R is commutative, then from this symmetric definition, if you have, then in fact this is isomorphic to this thing. This just does not make sense. This just doesn't make sense. Makes sense over not commutative ring, because over not commutative ring, no, you cannot interchange modules, because one of them is left and one of them is right. It's right, isn't left. But if R is commutative, then you have just this isomorphism of B modules. So it's isomorphic of chain complex, so it's isomorphic of homology, and we obtain that over commutative ring. Then we also have that Tor is commutative. It just follows from this symmetric definition. It's not obvious from not symmetric definition, but from this symmetric definition it's more or less obvious, because in fact you have isomorphism of these two B complexes. In fact, you can check this, but it's more or less obvious. So this symmetric definition is also useful. From not symmetric, it's maybe not obvious. Okay. And again, let's see again this argument. We see that in fact we use not projectiveness of P, we use flatness of PQ. So in fact, this argument says that we can calculate Tor, no, the same thing, by flat resolutions, because we only use flatness. We use that all this Tor between P and something are 0, and Q and something are 0. Okay. In fact, when we went from from the 0 page to the first page, we need that all this is 0, and this is use flatness of this module.
Yes, I agree. And by the way, since you're writing, like HP, and said that we don't know yet that this is indeed the Tor. So, okay. So we define a Tor like of we can define Tor as homologies of P dot tensor n, or.
Okay.
So you see, we can need to calculate the zeros for another definition.
Okay, if we consider some, I don't know what letter use, some flat resolution of M and some projective resolution of N, then this construction tells you that you have equality isomorphism of these two things. Sorry. n. And this is by definition Tor. And the same for the flat resolution of the another thing, okay? And if you know this, you also have used two flat resolution and their tensor product, okay? If you know that you can use one flat resolution and another flat resolution, then you can use them both, okay? So in fact, you obtain that it's isomorphic to homology of some flat resolution of n, flat. No, and of course, it's isomorphic to tensor product of flat resolutions. Moreover, in fact, you can use not just flat resolutions. Moreover, maybe a little bit mess here, but it's from all. Okay, maybe okay. I guess maybe what from this definition. What here, in fact, I don't need even that T is flat. In fact, I only because why? Because these elements on the first page, it's not Tor with anything. It's Tor, not zero Tor, between T dot and n, fixed n. So in fact, the same argument says you that if you have resolution, exact sequence, of such modules that Tor non-zero of this module and another module is zeros, then you can calculate Tor with this resolution. This called something like, I don't remember how it's in English, it's something like приспособленный резолвент. Ну, в общем, неважно. Okay. So if you have resolution of module such that Tor of modules of these resolutions, all non-trivial Tors, with some another module are zero, then you can apply this resolution of M to calculate this thing as Tor. Okay? Do you agree?
Yes.
No, and for another module also. No, and all these things works for X, but for X you obtain co-chain complexes, and then you need to use degrees in filtration and cohomological type spectral sequence, but all of this works, and for X you obtain that X and Mn can be calculated by such resolution of M such that all non-trivial X of P and N I0. Sorry, я написал какую-то ерунду сейчас. It's cohomology of form. It's co-chain complex hom from P to N. If you have no X here, then it's the same thing. No, and for example, if it's projective resolution, or it's cohomology of hom from M to some resolution of N, resolution of this form, no, such that all higher X between M and I0. Okay? By the same argument. Okay. No, and maybe the most general thing, it's an exercise. I leave this as an exercise. Okay, no, something like exercise. If you have some chain complex, which is bounded below, so it ends by zeros from some step. And this chain complex has only one non-zero homologies, so all homologies of this chain complex are 0, and only non-zero it's some module M, zero homology. Then you can use this to calculate Tor. But no, if you consider then Tor, Tor between M and N can be calculated as homologies of B complex of tensor product of this complex and some projective resolution of N. No, it's more or less easy exercise. Of course, maybe you cannot use this to just tensor with N, but if you tensor with projective resolution, then it works. No, and the same thing for X. For X, in the same manner. Okay, so you can use something like this. If you want, you have your favorite chain complex with your favorite homologies, then you can use it to calculate Tor or X. Okay. No, I think it's all what I didn't prove. Yes, the coincidence of the definition of Tor indexed. Yes, and now we obtain it easily from spectral sequence. Okay. Okay, I think yes. Maybe now I can. Yes. For example, no. Okay, I will say this in seminars. Okay, now about change of ring spectral sequence. Change of rings spectral sequence. It's important example of spectral sequences. Let we have. No, it's easy, but it's important. For example, let we have ring homomorphism. And that, no, now I want to compare Tor of extension and extension scalars and restriction of scalars. Okay, something like this. Let n is let n is S module left or right. No, sorry. No. Yes. Let n is right. Okay. N is right. R module. And M is left. No, what the heck? N is left. No, it's not important, but I want to obtain the formula of the appropriate form. N is left R module and M is right S module. Okay? No, let's see. Okay. Okay. No. Consider the projective resolutions. I consider S module projective resolution of M and R projective resolution of N. So I have projective resolution of right S modules of M and left projective resolutions of N. Okay. No, and consider the tensor product, but tensor product. Tensor product. B complex is tensor product over R. I consider this as R modules by restriction of scalars, and consider their tensor product over R. And I want what? And now I want to consider two spectral sequences of this B complex. one of these spectral sequences, the first one, it has these elements P, R, U, Q with vertical differential. With vertical differential. Yes. What is homologies of this? Think with vertical differential. What's homologies? What the first page is homologies of this thing. What it is? What Tor? It's not Tor because why is not Tor? No, no maybe.
N times R once again, no?
What?
I mean, once again we obtain what we got in the previous time, N times R.
But this thing. No. Yes. Sorry. You're right. Yes. You're right. Okay. Okay. Then it's. Yes, you're right. Sorry. Yes, Q is just projective. Yes. It will be a question about the second spectral sequence. It's just a projective resolution, and so we obtain Tor. Yes. No, it's not Tor. It's just because it's projective, so we obtain only one non-zero. Yes, thing because Q is projective. So no, sorry. Yes, no. You want to say that it's Tor between P and N? Yes? No, it's right, but we don't know what is it. We don't know what is it, but I can say that it's this thing. Do you agree?
By definition.
No, it's more or less obvious. Yes. No, it's about equality of these two modules. And okay. And now P it's S module. So it's something like this makes sense because Q is just R module and P is itself S module. Okay. No, the previous does not sense. The previous didn't make sense. My Q is R module and P is S module. Okay. So I have this thing. And now. And now P is S projective, so I have zero Tor because I don't know Tor over R of P and something because I don't know what P is as a model over R, but I know that P is S projective. Okay. P is S projective, so in fact, this thing. Tensor product with P over S preserves the homology of this chain complex, okay? Because P is S projective. And so it's S flat, okay? So in fact, this thing is equals to Q homology of P tensor S, Q homology of this thing. It's because P S flat. It's maybe not R flat because so I cannot do this before, but now it's S flat and I can do this. And now what these homologies? And this is Tor between what and what? Q Tor over R between S and N. Between S and N. From this definition, you see that you have, in fact, S-module structure, left S-module structure. You have left S-module structure on this chain complex, so you have left S-module structure on this homology. So you have left S-module structure on this Tor. N is right R module, N is left R module, S is right R module, so you have this Tor as a Billion group, but you also have left S-module structure on this Tor, okay? From this thing. No, and again, the second page of this spectral sequence, you calculate homology with respect to differential in P. So the second page of the first spectral sequence, what's the homology of this thing? It's over S. No, it's Tor between M and this S module. Over S. It's P over S Tor between M and Tor Q over R, S, and N. Second page. Okay, let's calculate the second spectral sequence. It's all what I needed from the first spectral sequence. Let's calculate the second one. Yes, maybe it's QP. It's homology of of the same thing, yes. But now I calculate under the first differential, and now I remove this. Okay, but now my Q is R projective. It's resolution of my N left R module, which is on the right, but it's left R module. Yes, and so it's projective, so it's commute with homology. So in fact, here I can write this thing. No, and here it's a homology of resolution. My P, it's exact. It's exact sequence of S models, but it's exact. So in fact, it has no homology except of the zeros one. So in fact, this is 0 if P greater than 0 and and less of 0, of course. It's all our spectral sequences are of the first quadrant. And M tensor Q if P is 0. So, and now P is number of column. Yes. I have only one. Sorry. It's number of row. Yes. I have only one non-zero row, and in this row I have M tensor Q. And another differential is horizontal one. And now if I calculate this thing, it's by definition Tor over R between M and N. So the second page, and it's infinity page because it's only one row. It's just Tor over R. It's Q over R between M and N, where I restrict scalars from my M module to R module. Okay, and again, there's only one row, so infinity page is the same thing as the target thing. So in fact, this is isomorphic to Q homology of this total complex. But this spectral sequence converge to this thing. So we obtain that there exists spectral sequence of this form. This is the spectral sequence of change of base, change of rings. If you have map of rings and you consider two modules, one over R and 1 over s. Then you can, if you want to calculate Tor over R, then you have spectral sequence, which starts from Tor over s between m and Tor Sn, something like this.
Why do we have there p plus q?
What?
Why do we have there p plus q? Tor p plus q.
No, because it converges to h plus q homologies of total complex.
Ah, okay.
Yes. It's by definition of spectral sequence. For example, no, it's easy to see, but for example, if S is flat R modulo, this means that calls that a homomorphism is flat. Then it is 0 and you have only one non-zero row and you have coincidence. If, for example, if S is flat R module, then you obtain that Tor and S M S tensor n is only 0 Tor here tensor isomorphic to Tor R. No, this is in fact more or less obvious from definition, but this is easy exercise and this is generalization. No, and exercise do the similar things for X. So obtain a change of rings spectral sequence for X. It will be the question on the exam. No, it's the same. In the same manner, you consider, if you have two chain complex, you also can consider home from one to another. It's also B complex, total complex, and you have spectral sequence and so on. Okay. Change of rings spectral sequence. No, this is useful in commutative algebra and algebraic geometry. It's a useful thing. Because in algebraic geometry, this restriction and extension of scalars have geometric meanings. And this Tor is, or X is some cohomology, some shifts, and something like this. And of course, this algebraic starting point is very useful. Okay. Now let's prove Kunneth spectral sequence. What's the Kunneth spectral sequence? Theory. Let we have two chain complexes which are bounded below. I have one chain complex which ends by zeros, and another chain complex which ends by zeros. Such that relative Tors are 0. So these modules are relatively flat. This means that all higher Tor between what is it? Yes. Between these two modules are zeros. Okay. So for example, one of them is flat, of flat module, something like this. Then there exists spectral sequence with this second.
These chain complexes are infinite to the left.
Yes, left, of course. Bounded below. No, like projective resolutions.
And you mean
For every
ij, yes?
Yes, yes. No, for example, one of them is one of them is of flat modules, okay? then there exists a spectral sequence of this form. No, it's all over some one ring. You can compute homologies, and if you consider Tor between homologies, then its spectral sequence converges to homology of tensor product of these two chain complexes. If you want to compute homology of chain complexes, if this chain complex is not very bad to each other, then you have spectral sequence which starts from Tor between homologies. Okay? Now let's consider our resolutions to our two chain complexes. I have resolutions. Not sorry. Here I want that I is number of modulo and dot is number of level of resolutions. And for L, Q dot J. It's our constructed before Cartan-Liebenberg resolutions of chain complexes. I consider, no, it's B complexes by definition, these things. So I consider T, I consider total complex of one of this, total complex of another, this. It's chain complex, and I consider its standard product. It's as B complex, as B complex. No, unwinding definitions, it's just this direct sum. K plus L is P, I plus J is Q, P, K, I, tensor Q, L, J. And I have two differentials here. This is differential of T. It's a horizontal one. It's now let me denote, for example, horizontal differentials here. I will denote D, P, and vertical one is D, P. Okay, D here D is differential in projective resolution, and here differential is this chain complex. It's splitting differential. Okay, and so this horizontal one, it's sum of horizontal differentials. It's dp plus with sign of differential of another one, and vertical is for vertical. Okay, if it's not obvious, then it's an exercise. Okay, and now I want to again, I want to do the same thing as I did for change of ring spectral sequence. I want to consider two spectral sequences of this B complex. One of these spectral sequences gives me tractable second page, and another gives me tractable target. It's kind of usual trick. Okay. No. Maybe I leave this property assumption. Okay, what the first page of the first spectral sequences? P homology of my T H. Again, I am here. Maybe I mixed vertical and horizontal ones. 0 must be vertical, so it must be vertical differentials. Okay, this is the first one. Okay, I want to compute this one. I want to compute the horizontal differential first. With horizontal differential. Сейчас, horizontal differential. Then it's must be QP. Yes, QP. I start with horizontal differential. Okay. And what is it? What is homologies of the horizontal differential of this B complex? No, it's I fix my Q, so I can use this Q. I can move this direct sum of a Q from homology. So in fact, it's just direct sum I plus J is Q, P homology of tensor product P. No, yes, it's tensor product of these two chain complexes. Is I and J fixed the horizontal differential. And what these homologies? No, this differential, horizontal differential, is kind of splitting differential. Now let us an exercise for the next time. Exercise. If I have two chain complexes bounded below, and such that they are splitting chain complexes, which means that no differential in them looks like I have something, homologies, something, and differential goes. This goes to 0, and this goes to bi minus 1. Okay. I call such chain complexes splitting chain complexes, and if you have two splitting chain complexes which are bounded below, then in fact homology of their tensor product, it's a very particular case of Kunneth spectral sequence, but no, we need this particular case, and you can check this directly. What's homology? What do you think? What do you think? What's homology of these things? No, it's tensor product of homologies. No, something like n, then it's direct sum. A plus b is n, HA, HB. It's an exercise. Now I have such two differentials, such two chain complexes splitting, because I use now horizontal differentials. So it's, no, it's, yes. I plus j is q. I consider p homology. Yes. No, maybe yes. I don't. And now what's homology of this chain complex with horizontal differential? It's this homological part of these resolutions. It's the resolutions of homologies, in fact. Yes. It's homology of P H tensor homology of Q H. Did you remember what is this? Do you remember? It's homological part. I have my resolution, and this resolution have form B homology and B dot minus 1. And this is the resolution of homologies, in fact. And this is homology of the with respect to the horizontal differential. Okay. So this is my homology with respect to horizontal of P, horizontal of Q, and I have this thing. Okay. But now I want to compute these homologies with respect to vertical differential to obtain the second page of this spectral sequence. And this is tensor product of two projective resolutions of homologies. And if I calculate the homologies, I obtain Tor between homologies, as we've seen before. Because this is this is projective resolutions of homologies of K, this is projective resolutions of homologies of L. Okay? So, second page, Q, P. It's something like Q. What is? I'm not sure. It's Q, P, P, Q. Okay. But it's Tor, P Tor. Between homologies. Yes, between. No, yes. Yes. In fact. Sorry. Yes. It's. No, it's resolution, but it's resolution of. No. It's resolution of E homology of K, and this is resolution of J homology of L. So it's Tor of E homology of K and J homology of L. This is the second page. Okay, I will say it the next time with the correct index. Okay, and it's second page. Okay, and now from the considering the second spectral sequence, I obtain the target. For the second spectral sequence, no, for the first, I have that its homologies with respect to vertical differential at first. Okay, ну ой, почему-то тут поменял, ну ладно. P with respect to vertical one first. So yes, then it must be okay. Vertical differential might be complex. It's stop. It's very weird. 1 second. If I have big complex, maybe if I have big complex, if I consider I need this differential, and this differential is with respect to the second one. It's true, and I consider P homology. Sorry. No. Just 1 second. Here it's correct, but then here it will be between the horizontal one. It's horizontal. No, yes, it's stop. It's strange. Q homology of vertical one. Okay. Okay. And what is it? What's homology with respect to vertical differential of this big complex? No, again, it's just it's direct sum. Now, with respect to K, because K is fixed here, K plus L is P, and now it's Q homology of this tensor product P K dot tensor Q L dot with respect to vertical differential. I consider and now I consider two projective resolutions of K, K and L, L. Consider the tensor product and compute homologies. So I now just compute Tor between K, K and L, L. Okay. Between this things, it's this this thing is the resolution of K, K. So this homology is just Tor, and I know that all these Tor are 0. Except of the 1 degree. So in fact, this is 0 if Q then 0 because it's Tor. It's Q Tor between K K and L L. And tensor product K K and L L if Q is 0. So I obtain spectral sequence with only one non-zero, I don't know, row again with these elements. Sorry, direct sum, yes. K plus L is P. And I have some differential. And this differential is exactly differential integral product of these two chain complexes. It's a horizontal differential. And if I compute homologies, then second page, or the first one, is the same as the infinity page. It's just homology of my tensor product of my two chain complexes. No, so I have my target and I have my spectral sequence. Okay. About indexes, I will say you the next time. Okay? So we obtain spectral sequence. We have two spectral sequences, but we consider one of them, which gives us the second page. Another spectral sequence, they kind of degenerate. So no, if you have degenerate spectral sequence, of course you can say something about target, but you cannot say something new. Here you can say something new because you have second page, and if it's some, maybe it's some zeros here, or maybe you can even say something about differentials here. But you know that it converges to the same thing as the second spectral sequence. The second spectral sequence converges to this thing, to homologies of the tensor product. So you know that this spectral sequence also converges to homologies of spectral sequence of tensor product. Okay. So we obtain this spectral sequence which converges to homologies of tensor product of chain complexes, if this assumption holds. No, and also, no, it's kind of exercise. You can do you can do the same thing for X. You can consider, if you want to calculate homologies or cohomologies of Hom between two chain complexes, then you obtain spectral sequence of X. Kunneth for X. No, it's kind of exercise. Kunneth for X. If you have two chain complexes, such that maybe X are 0, so one of them injective, or for example, another is projective, then you have spectral sequence consists of X between homologies, KL, and some direct sum, which converges to homology of Hom. No, it's an exercise to correctly formulate it and prove. No, proving the same thing. And yes, and important exercise here to check that for splitting complexes, homologies of tensor product is tensor product of homologies. It's important here. We used it here. Okay. It's the simplest case, but we need to check this. Okay. Kunneth formula is a particular case of Kunneth spectral sequence. No, it's the same case as I said before. If you have in spectral sequence one row, you have obvious case. If you have two rows, you in fact obtain short exact sequences, and this is the case. This is the case when our spectral sequence degenerate to only two non-zero rows or two non-zero columns. No, namely, let no, we have the same things. We have K, L bounded below and relatively flat. No, this is, the same assumptions which hold for spectral Kunneth spectral sequence. Okay. Because we need it. We need spectral sequence. And let me assume additionally that, for example, for one of these complexes, for example, L, this is true that we have, as I said before, I have cycles of L. It's L and it's boundaries of L. Let me assume that these modules are flat, and if I assume that this module is flat, then the flatness of these two modules are equivalent, because if one of these flat, then third from the two others, as we discussed before, is flat. No, so one of these two flat. So this flat and one of these two flat. No, this is equivalent to this, that all is flat. So all this flat, in fact, flat. All models are flat. No, in fact, no, yes. Yes.
Wait, why are all of them flat?
No, it's my assumption. I just said before that, no, in fact, I can assume only that one of these is flat, but then they all three are flat, if this is flat. So in fact, I have all my models are flat. Yes. No, for example, they're free. If you over principal ideal domain, then if Li is flat, then these things is submodules of flat, then they are also flat. For example, for abelian group, this is torsion free, and then this is submodules, then also torsion free and flat automatically. All these things are just say that one of my chain complexes is of flat modules. But over general ring, it's additional assumptions. And my assumption is that my modules are flat, my cycles are flat, and my boundaries are flat. No, but boundaries is less trivial because it's quotient. No, but okay. Then, if it is true, then this thing it's flat resolution of homology of length 2. So in my spectral sequence, if I have flat resolution of length 2, then for Hj, non-zero only P1 and P0, and all higher are 0. So in this spectral sequence, I have only 2 non-zero columns, or rows, if I write down not correct indexes. No, it's not important. Okay, no, let's, in this interpretation, let's I have 2 columns, okay? P1 and P0. I have only 2 non-zero columns. The first column, on the 0 column, I have, no, it's kind of tensor product. No, okay, no, it's H, I, H, J, and this is Tor such that I plus J, some Q, some Q, some Q. Okay. No, and let's see what does this mean. I already have, no, it's also have that, it's second page, but because I have 2 columns that are neighbors, and then all high differentials also 0, so all differentials more than unwent. And the second differential is also 0. All high differentials are 0, okay? Because they have something like this. Sorry. Something like this, but okay. Because they have b degree minus r1 minus r minus 1. And if this thing is greater than 1, then it промахивается. Так, okay. So this is infinity page, in fact. And again, if you in infinity page have 2 columns, then you have only 2 non-trivial quotients in your filtration on the target, on homologies of tensor product. And this means that you have only one extension, only one short axis sequence. And this short axis sequence of the same form. You have E infinity where P is 0, this thing, which is N, H, A, K, tensor J, L. It goes to N, K, tensor L. And quotient is E infinity of the same diagonal. So it has I plus J is N minus 1. Okay, N minus 1. Tor, no, the only non-trivial Tor between the same homologies. Now this is Kunneth formula for flat, for good enough chain complex, one of them. This spectral sequence degenerates to this short axis sequence. So homology of tensor product is between tensor product of homology and this is this thing. Mm-hmm. Yes, sorry. Погодите-ка. Yes, and from this formula, you can see that the previous exercise was wrong about splitting complexes. Because this formula says that in any case, if you have non-trivial Tor between homologies, you cannot have that tensor product is the homology of tensor product. Okay, even if it's in our situation, our complexes are projectives, and all homologies are projectives. So in fact, here is 0 because. So yes, sorry. Exercise is we have two chain complexes bounded below, and they are splitting, and they are of projectives. It's an important additional assumption. It's bounded below, projective, and splitting. Then homology tensor product. It's homology of tensor product of homologies. Yes. No, we see that it is. Agrees with this formula, but no, of course, this formula is from spectral sequence, and spectral sequence is from this fact. And please check it directly. Mm-hmm. No, in our case, we consider tensor product of projective resolution, so all our models was projective. So projective.
What do you mean by splitting?
Splitting a chain complex is it has direct sum of kernel and image. Image goes to and kernel it's the previous image and homology. And this goes to 0. This goes identically to this one. Okay. Chain complex with differential of this form. All my models are direct sums. Differentials acts by this rule. Okay. And all these models are projectives. No, it's equivalent to say that this model is projective because it's direct sum of projectives. Yes. Okay. No, and also you have the same formula for X. The same formula for X, which relates homology of home from homology to homology, and X. First X from homology to homology if all higher X are zeros, for example. No, in fact, this means that it's not about flatness, of course. It's about something like boundaries. All boundaries, cycles, and L are projectives for left one or injectives for left one. If you consider home here, yes. No, it's a dual statement. It's also exercise. So that's what's about text. What about text?